What if you could travel to a place where time slows down and space stretches? Welcome to the intriguing world of black holes. In the vast cosmos, these celestial bodies are one of the most perplexing phenomena, captivating the curiosity of astronomers and physicists alike. To understand black holes, we must first grasp the concept of space-time. Picture this, a rubber sheet stretched tight. Now place a heavy ball in the center. The sheet dips under the weight, right? This is a simplified analogy for how mass distorts space-time. The heavier the object, the deeper the dip or curve it creates. Now let's talk about stars. You see, a star is a delicate balance of forces. The inward pull of gravity trying to collapse the star is counteracted by the outward push of nuclear fusion reactions at the star's core. As long as these forces are in equilibrium, the star maintains its shape. However, when a star exhausts its nuclear fuel, this balance is disrupted. The outward pressure drops and the star collapses under its own gravity. What follows is a spectacular supernova explosion, and what remains is a core so dense and gravity so strong that nothing, not even light, can escape its grasp. This star-turned prison, ladies and gentlemen, is what we call a black hole. These celestial enigmas are like cosmic vacuum cleaners, sucking in everything that ventures too close. But they don't just swallow matter, they also distort time. Near a black hole, time ticks slower compared to further away. This is known as time dilation, another mind-bending effect of intense gravity. We've come a long way in understanding these cosmic entities, yet there is so much more to uncover. So black holes are not just a figment of science fiction, they are very real and they are right up there in the cosmos. What lies beneath the surface of these cosmic phenomena? Let's dive into the anatomy of a black hole. Imagine a whirlpool, a swirling vortex of water that pulls everything down, and you've got a rudimentary picture of a black hole. But instead of water, it's space and time drawn into an infinite descent. This whirlpool has three distinct parts: the outer event horizon, the inner event horizon, and the singularity. Let's start with the outer event horizon. This is the point where the pull of the black hole becomes so strong that nothing, not even light, can escape. It's the boundary of the whirlpool, where water starts to spiral down. Once you cross this invisible line, you're on a one-way trip into the black hole. There's no turning back. This is what we often refer to as the point of no return. Further in, we encounter the inner event horizon. This is where things get really weird. The laws of physics start to behave in ways we wouldn't expect. It's like the faster, deeper part of the whirlpool, where the water moves in unpredictable ways. Here, space and time switch roles. Space becomes time and time becomes space. It's a realm of extreme tidal forces and intense radiation, a place where reality as we know it gets twisted. At the very heart of the black hole, we find the singularity. This is the point where all the matter that has fallen into the black hole is crushed into an infinitely small, infinitely dense point. It's like the bottom of the whirlpool where everything that's been sucked in ends up. But unlike the whirlpool's bottom, the singularity is a place of infinite gravity and density. It's a place where our current understanding of physics simply ceases to exist. The heart of a black hole, the singularity, is where our understanding of physics breaks down, making them even more intriguing. So, what happens if you get too close to a black hole? Well, it's something straight out of a sci-fi movie. When objects get too close to a black hole, they don't just disappear. Instead, they undergo a process that physicists have lovingly termed spaghettification. Imagine you have a piece of dough in your hands. If you pull it apart, it stretches, right? That's essentially what happens to objects that fall into a black hole. The gravitational pull is so intense that it stretches and distorts anything that comes within its grasp, turning it into a long, thin strand, much like a spaghetti noodle. But it's not just physical objects that black holes affect. They also have a profound impact on something we all take for granted: time. Now, this is where things get a little mind-bending. According to Einstein's theory of relativity, gravity can bend time. The stronger the gravitational pull, the more time slows down. So, near a black hole, time would theoretically slow to a crawl. Imagine you're floating near a black hole while your friend watches from a safe distance. To your friend, it would seem as though your movements are occurring in slow motion. But for you, time would appear to be running normally. This is because the immense gravity of the black hole is distorting time itself. And it's not just a time distortion. If you were to look towards the black hole, you'd see a distorted view of the universe. The immense gravity bends light itself, creating a warped view of the cosmos that would be both terrifying and awe-inspiring. So, black holes are more than just cosmic vacuum cleaners. They are mind-bending enigmas that can stretch matter, distort time, and warp our perception of reality. They are a testament to the strange and wonderful universe we live in, and a reminder of how much we have yet to understand. In the vicinity of a black hole, you would experience some of the most extreme conditions in the universe. Despite their ominous reputation, black holes could hold the key to understanding our universe. As we dive deeper into the abyss of black holes, we find they're not just cosmic vacuum cleaners, but rather they're celestial laboratories where the laws of physics are tested to their limits. They are the key that could unlock our understanding of the most fundamental aspects of our universe, like gravity and space-time. Think of gravity not as a force pulling objects together, but rather as a curve in space-time caused by mass and energy. Now imagine a black hole, an object so compact and dense that it literally punches a hole in this fabric of the universe. By studying black holes, we can gain insights into the mysterious nature of gravity, pushing the boundaries of our understanding of Einstein's theory of general relativity. But black holes don't just help us understand gravity, they also play a crucial role in galaxy formation. It's like this: galaxies are massive, containing billions of stars. At the heart of most galaxies, there's a supermassive black hole acting like an anchor, around which these stars revolve. This gravitational powerhouse might be responsible for the galaxy's structure and might even have a say in its evolution. Now let's talk about something truly fascinating: Hawking radiation. Proposed by physicist Stephen Hawking, it suggests that black holes aren't entirely black. They emit tiny particles, a kind of radiation, due to quantum mechanical effects near the event horizon. This process could, given enough time, lead to the evaporation and eventual death of black holes. It's a concept that blends the two pillars of modern physics, quantum mechanics and general relativity, further reinforcing the importance of black holes in our quest to unify these theories. Black holes, the ultimate destroyers, might also be the ultimate creators. So the next time you gaze at the night sky, remember that these enigmatic entities aren't just cosmic calamities. They're cosmic clues, waiting to unlock the mysteries of our universe. As we stand on the brink of exploring the final frontier, black holes continue to baffle and fascinate us. These cosmic phenomena, once thought to be mere figments of theoretical physics, have now become a central focus of modern astrophysics. They are the unknowns, the uncharted territories of our universe, drawing in the brightest minds like a gravitational pull. Today, research on black holes is more active than ever, with scientists around the globe striving to decode their mysteries. The Event Horizon Telescope project, for instance, aims to capture the shadow of a black hole, and in doing so, provide us with the first ever direct observation of these cosmic enigmas. Such endeavors are not just scientific pursuits, but quests for understanding our universe and our place in it. Black holes are more than just cosmic vacuum cleaners. They are, in fact, key to understanding the fundamental laws of physics. Their existence challenges our understanding of reality, pushing the limits of what we know about time, space, and matter. They are the playgrounds of quantum mechanics and relativity, two of the most profound theories of physics. However, studying black holes is no easy task. Their very nature makes them nearly impossible to observe directly. We can only observe their effects on nearby objects or detect the radiation they emit. This makes them one of the greatest challenges in modern astrophysics. But with each challenge comes opportunity. Black holes could hold the answers to some of the most profound questions in science. What happens at the singularity, the point of infinite density at the center of a black hole? Could black holes be gateways to other universes? These are the questions that drive us, that push us to explore the final frontier. In the end, black holes are not just about destruction. They're about creation, about mysteries, and about the endless possibilities that lie in our universe. As we continue our cosmic journey, we look forward to the day when we can truly say we understand these enigmatic giants of the cosmos.